very much.
Thank you all for coming out. It's been Phoenix, none of you have been here with a snowstorm. But this isn't a snowstorm for you, I know. So, but thanks anyway. It's a pleasure to see all of you tonight. And I hope we'll have some fun. I'll stare at that thing staring at me, but it's okay. I put on some stuff that's primarily so you could have him to read while I was being introduced, which I find is useful. But this actually is one of my favorite quotes because it epitomizes to me this. I'm going to try and move this down. It's a little loud. In fact, I'll put this volume down a little bit. Maybe.
We can't hear you.
You can't hear me? Now you can?
Yeah, it's better.
Okay. See if it. Okay. Good. Well, you let me know. If you can't hear me, you're not missing anything, so it doesn't matter. I guess I can. Okay. We'll see how. Well, maybe these things are turned on. Anyway, I like to get close, so I don't want to be stuck back there. In any case, this is one of my favorite quotes because it epitomizes what science is all about and what I want to talk to you about, which is really ultimately a mystery story. But the biggest question is, of course, how we got there in the first place, which is, in this case, the question of why is the universe here? And why is there something rather than nothing? That's a question that's been around for as long as people have thought about questions. It's traditionally been a religious or a theological question, but it isn't a religious or theological question because, as I'll point out, something and nothing are physical quantities, and therefore it's a scientific question. And science has completely changed the playing field of that question. Now, maybe this is true in Calgary. I used to live in Cleveland, and I used to have to tell people that these are stars. But, I don't. But the universe is remarkable. Look out at the night sky when it's clear and you're away from the city. And it is remarkable. It's a globular cluster, but it doesn't really matter whether you're looking at that or anything else. And as beautiful as it is, what we've learned in the last century or so is that all the stuff we can see is just the tip of the cosmic iceberg of stuff we can't see that has changed our picture completely of not only the present universe, but the past and the future, as I'll describe. And changed our picture, in fact, of as we get closer and closer to understand, perhaps, how the universe began. And what I want to talk about tonight is an amazing result, a series of results, that in fact, we now plausibly can understand how a universe could come from nothing. And it seems to me that is an idea that is ultimately worth celebrating, as I'll describe. So, this question has many different ways of answering it, as I pointed out. There's a lazy answer, which is this one. That doesn't tell you anything. It doesn't explain anything. It's just ultimately an intellectual cop-out. And what is really important is if we really want to understand how the universe began, we should look at the universe and not just think of it or get a revelation. So we really want to look at that universe of stars. And that has caused us, over the last century, perhaps in one of the most exciting intellectual roads and struggles, step by step, to come up with a picture of the universe which is stranger than we could have ever imagined. That's the other thing I want to emphasize tonight, is that the universe is indeed stranger than we can imagine. And the actual universe is far more interesting than the universe of myth or fairy tales. And I can't understand why people seem to think it's somehow less inspiring than words written thousands of years ago by people who didn't even know the Earth went around the sun. In any case, so let me begin slightly differently on this mystery story. It was a dark and stormy night. Now, by that, I'm not referring to the beginning of the universe, but rather to the night that Albert Einstein dotted the last period on his most famous set of equations, most important set of equations, his discovery of the theory of general relativity, which was a theory not just, was a theory of gravity, but it was actually much more than that. It was a theory of space and time. It was the first theory of space, in fact, but it was not a theory of just how objects move through space, but how space itself. Damn this thing. Well, I'm gonna, you know what, you gotta see if you can turn that off. That might be causing that. Is your, you introduce me. Where's your microphone off? Where are we going? Okay. Well,
It's off.
Okay. Anyway. So it was not just a theory of how things move through space, but how space itself moves. Space in fact, according to general relativity, is dynamical. It responds to the presence of matter. And it's a beautiful theory, and in fact, since it was a theory of space, it was the first theory of the universe. And Einstein knew it was, and he knew it was right. There was a small problem, however, and that was that it didn't describe the universe in which we lived. Nowadays, that doesn't seem to bother physicists too much, but it used to. And Einstein was quite worried about that, and he revised his equations in a way to accommodate that. He was a very creative guy, and he realized he could revise them in a way that was consistent with all the symmetries that had led him to develop these equations, and it could describe the universe in which we lived. In 1916, the universe in which we lived, in which Einstein lived, was static and eternal. Conventional scientific wisdom was that the universe had been around forever and would be around forever in more or less the same way. If you look at the stars night after night, they're the same. So it seems reasonable to assume that. But there's a problem. And there was a problem with general relativity, and there was a problem with Newtonian gravity. Anyone who's taken physics knows that gravity sucks. It always pulls. It never pushes. And if you put a bunch of stars out there, you wait long enough, their gravitational attraction will all cause them to collapse together. And you couldn't have a static universe. Things wouldn't stay there. So as I say, he revised his equation just a little bit, and I want to show you how. And we'll try and lock the doors now. Okay. I want to show you Einstein's equations. Now, I've written them in a user-friendly form here for the biologists. There we go. Turn it down a little bit. I was thinking I was going to do that myself. Okay, let's see if we get feedback. Let me walk here and see if we get feedback. Well, not as bad. No, hear it? I hear it. Does this mean I'm going to... Yeah, that mic is not on, I think.
I think it's from the speaker.
Could be from the speakers. Okay, I'll stand behind the speakers. The speaker will stand behind the speakers. Are we okay? Okay. I got this one on. That was from my computer. So. Okay. Let's see. That may be a little bit better. It's a little bit less loud. Can you still hear me?
Yeah.
That's much preferable. Okay, good. I think we got it. Okay. So, now you've had time to stare at this equation and work it out. And it's a little easy. The left-hand side is equal to the right-hand side, but it's not completely facetious. Because in general relativity, the left-hand side relates to the geometry of space. Space itself can curve in the presence of matter. So all the geometric quantities are on the left-hand side, and the stuff that causes the curvature of space, the energy and momentum of stuff within the universe, is on the right-hand side. So this is the physical content of Einstein's equations. I'm a theoretical physicist, as was pointed out, and therefore I have to write down the Greek letters. There, that's much more illuminating. Now, this was the equation that had the problem, because this is the equation in which gravity sucks. And so Einstein realized that he could add an extra term to the left-hand side of the equations. And it's a term he called the cosmological term. And this term would produce a small repulsive force throughout all of empty space. So small, it wouldn't affect any of the results of the planets orbiting the sun, the beautiful results that led Newton to his theory of gravity. But on the other hand, it could build up over the scale of the universe and perhaps hold distant stars apart. So he thought this would result in a static universe. And the problem was, of course, lots of problems happened. And in fact, almost immediately after he wrote it down, he called it his biggest blunder. This is one of the reasons. This was a postcard I got when I was on sabbatical a bunch of years ago in Switzerland, from Einstein to Hermann Weyl, in 1923. And Einstein said to Weyl, Weyl was a famous mathematical physicist, if you get rid of a quasi-static universe, then out with the cosmological term. Because he realized already in 1923 it was beginning to be understood that the universe wasn't static. And if you have this universe that isn't static, you don't need this universal repulsive force. Because if the universe is expanding, in fact, gravity can be purely attractive. It can slow the expansion of the universe and maybe stop it and cause it to recollapse in the reverse of the Big Bang, or not. And that became the central question of 20th century cosmology, is how will the universe end, with a bang or with, basically. And he realized he didn't need this term anymore, and he wanted to throw it out. He called it his biggest blunder. Now, already, as I say, by 23, he was people were beginning to think the universe might not be static, but the person who fits the world of this is this man here. He's one of my heroes. He's one of my heroes because he gives me faith in humanity, which I desperately need at the present time. Because he began life as a lawyer and became an astronomer. So there's hope. And, but he did many, many things. One of the first things he did, which is actually somewhat peripheral to what I want to talk about, but probably worth mentioning, is well, up to that point with large telescopes, in 1925 he was using the Mount Wilson telescope, newly built. And up to that point, if you looked at our galaxy with the largest telescopes then available, you'd see stars, and then you saw these little fuzzy things, which were called nebulae, which is Greek for fuzzy thing. And there was big debate about what they were. And what Hubble was able to show, in fact, in 1925 with the Mount Wilson telescope, is that actually he was able to distinguish stars in them and discover, in fact, that there were other island universes, other galaxies. Until that point, until 1925, we knew of one galaxy in the entire universe. That was it. Our universe was the Milky Way galaxy. And we now know that there are over 400 billion galaxies in the observable universe. So in a single human lifetime, in 87 years, we've gone from 1 to 400 billion. We're like the early map makers. It's not surprising that we're surprised, in fact, and our picture of the universe is changing dramatically, and it's those changes I want to describe to you today. Now, the discovery of the expanding universe is important enough I want to describe it a little bit. So, what did he see? Well, he saw this. We're here, these are galaxies, not sperm. And so, if we're on our galaxy here, we look out, we see all the galaxies on average, and what Hubble saw is all of the galaxies on average were moving away from us with a certain velocity, and those that were twice as far away were moving away from us with twice the velocity, and those that were 3 times far away were moving away from us 3 times the velocity. So what does this tell you? It's obvious what it tells you. We are the center of the universe. That's what it looks like. It certainly seems that way. But as many of my friends remind me on a daily basis, that's not true. In fact, what it really means is the universe is expanding. But the problem is we're stuck in our galaxy. We're stuck in our universe. Well, most of us are. The Republican candidates aren't. That's an easy laugh. But in any case, so if we want to see what's happening, we've got to get out of our universe, and that's hard. But I can do it with the universe I can create on the computer, where I want to get outside the box. So I make this universe, a 2-dimensional universe. It's easy to draw. We're outside of it, and this is a region of it. And I put galaxies at nice uniform distances apart at time t1, and at some time t2, you can see they're a lot further apart from each other. The region has expanded. So if you were standing outside that universe, you would in fact see that it was expanding. But what would you see if you lived in that universe? Well, let's pick a galaxy, any galaxy. So to see what it looks like in that universe, I'm going to superimpose this image on top of this one, placing this on top of this. Okay. So what do we see? We see exactly what Hubble saw. Every galaxy is moving away from you, and those that are twice as far away have moved twice the distance at the same time. Those that are 3 times as far away have moved 3 times the distance, and so on. And it doesn't matter what galaxy you pick. You see the same thing from every galaxy. So depending upon your mood, either every place is the center of the universe, or no place is the center of the universe. It doesn't matter. It really doesn't matter. What it really matters is that the universe is expanding. And what Hubble discovered is the universe is expanding, and that was profoundly important. It changed everything, because it meant our universe had a beginning, which had profound implications for science, but it also had profound implications for theology and everything else. It meant our universe had a beginning. We now know that beginning was 13.72 billion years ago, except in Arkansas and a few other places. Maybe Alberta, I don't know. But it is 13.72 billion years old, and that is amazing, that we even know that to 4 significant digits. I never would have thought in my lifetime we would know that. But I want to tell you how we know it, because, okay, this is physics, not philosophy. So if you have this discovery, you're measuring things. You're measuring the velocity of objects as a function of their distance. Objects that are further away are moving away from us faster. So how can you measure this? Well, you have to measure velocity and distance. So how do you measure velocity? That's the easy part, it turns out. And these 2 cowboys know how to do it, one in the is talking to the other as they look at that train on the prairie, and one says to the other, "I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes through the Doppler effect." Because what they're talking about is the famous fact that when a train is coming towards you, the train whistle gets higher. When the train is moving away from you, the train whistle gets lower because, in fact, the waves stretch out behind the train. They scrunch up in front of the train. The frequency goes up in front, gets lower behind. For very different reasons, it turns out the same thing happens to light. So for objects that are moving away from us, the light from those objects gets stretched out to longer wavelengths. And the red end of the spectrum is the longest wavelength end of the spectrum, so we say they're redshifted. The ones moving towards us are blue shifted. And what Hubble discovered is that the objects that are systematically further away from us are systematically more redshifted. So that's easy. Measure the redshift, you know the velocity. But how did he know which objects were systematically further away from us? That's the hard part. That's always been the hard part in cosmology, because those objects are far away. We don't have tape measures that are that long. So we've got to think of some way to measure distance without a tape measure. And of course, we use the laws of physics. And I could measure the distance to the back of the room by turning off all these lights except for one, and say a 100-watt light bulb. And some of you are as old as I am here, you remember cameras that had light meters. And if you used to have a camera that had a light meter, if I knew there was 100 watts coming from that light, and my camera, I detected 1 watt, I know that the light spreads out in a certain way, in a well-defined way, and I can work backwards and figure out how far away that light bulb is. So if the universe were populated by 100-watt light bulbs, we'd be fine. But it isn't, so we have to look for something like a 100-watt light bulb, something we call a standard candle, something whose intrinsic brightness we understand. And then we look at it through a telescope and see how bright it looks. And if it's fainter, it's further away. If it's brighter, it's closer up. So we need standard candles, and that's the hard part. And in fact, it was the hard part when Mr. Hubble was doing his data analysis. This was in 1929. This is his original data for 1929. Velocity is a function of distance. And one of the reasons he was such a great scientist, in fact, was he knew to draw a straight line through that data set. It's not obvious that's the right thing to do. When he did, he got the rate at which the universe was expanding, and one of the wonderful things he did for us was he got it wrong by a factor of 10.